All right, so let's go ahead and get started with this thing. What we've got today is motion in 2 dimensions, our first briefing on Chapter 4 material. So I do want to kind of talk about how did we actually get here. In our last couple of lectures, Chapter 2 through Chapter 3, we had some different things going on. Right, first in Chapter 2, we were talking about how do we describe motion, but confined to 1 dimension, right? So we kind of got a little bit more familiar with things like position, with velocity, with acceleration, but in those cases, we talked about those being either positive, negative, or 0, one of those 3 options. And more than that, I also kind of mentioned that some of these things are vectors, but we didn't really define what vectors are. I really just kind of gave you the difference of there's velocity versus speed, there's distance versus displacement. There's a little bit of a difference between those. But Chapter 3 really started to characterize those things and describe, hey, you can have components. Here's what you can do with adding vectors and subtracting vectors, and moving things around and doing all sorts of things like that. And at the time, it was just numbers, I guess, right? Directions and numbers, specifically. But it didn't really have any sort of real tie-in with the things that we had been seeing before, right? I mentioned that some of these things were vectors, but we didn't work with them as vectors. And today, that begins to change. So when you start thinking about things in 2 dimensions, it becomes an instantly much more complicated kind of picture here. So our more complicated picture here, you can see that we have our position. We're going to call this the R vector, right? So this is our arrow here in black, still on the eraser. That's that one right there. That's a position vector, and we can see that there is an X and a Y component to that vector. Our velocity, similarly, has an X and just a little bit of a Y component to it. Our acceleration has an X and a Y component to it. All 3 of these are a lot more complicated than what we had seen previously in Chapter 2. The old relationships still hold true, though. Velocity is still just the derivative of our position. Acceleration is still just the derivative of our velocity, the rate of change of the thing up above it on the ladder. So, as we're dealing with these problems, I've got 2 things that I'd like you to consider. First is the trajectory of the object that we're looking at. This is going to be a really, really fantastic way to deal with how we are going to actually draw these things out and help visualize these things. So previously, we have been working with graphs like what we see down here. Both of these are not trajectory. Trajectory is what happens when you're trying to do something like a long exposure photograph, right? How many people have seen those? There's those really, really cool pictures where they've got like a picture of a highway and you can see like all of the red trails from where the car lights were and all the white trails where the cars are coming towards you, right? Stuff like that. Or maybe somebody has done a long exposure, but any of those long exposure kind of things, right? They're really, really cool. But what's happening there is that I'm not trying to characterize what happens in time necessarily. Maybe I can infer some details about time, but for the most part, what I actually have to deal with is the fact that I'm seeing all of the positions that this object went through at the same time. That's what a trajectory is. These are our old graphs. We can create trajectories from these things, but these on their own are not trajectories. So the reason that we like to do this is typically going to be a little bit more conceptual because we can kind of think about what's going on in our picture rather than having to deal with looking at these graphs. These graphs would probably give us more information, but the trajectory picture would tell us a little bit more about how we think the motion would go as we would see it. Right? If I tossed a ball to a friend or something else like that, I would imagine the trajectory is going to be a parabola. That's what I would experience over time. But in looking at the trajectory picture, it doesn't tell me anything about when it was in each of those positions. So that's one thing to think about here. The other thing that I would like you to think about is that velocity, acceleration, position, all of them, but especially velocity here, are going to be vectors. If we have any of these things, what we now see is that the velocity might not only be changing in magnitude, but also in direction. And that's a little bit funky at first, but think about something like this. So if acceleration is supposed to be the change of velocity, and velocity is something that has a direction and a magnitude, imagine you are driving around in a circle, or if you're on a merry-go-round or anything else like that. You are spinning around. You could argue you're spinning at the same speed. I would agree with you, right? Earth orbiting the sun is spinning at mostly the same speed. The difference, though, is that there's an acceleration changing the direction of that velocity. So the speed might not stay the same, or it might stay the same. The velocity with an acceleration is certainly going to change, but which components of the velocity change might depend on the acceleration. Whether or not the speed changes might depend on the acceleration. These are some details that we're going to have to be watching out for. And this change might be in some direction that is not like any of the other ones. So how do we actually deal with these things? Well, I'm going to be honest, most of what we're going to be doing from now on is going to continue using this. You might notice this as a trend. Chapter 2 stuff depended on the stuff we did in the first aid. Chapter 3 stuff, a little bit more independent, but Chapter 4 certainly depends on Chapter 2 and Chapter 3. 4, 5, and 6 all depend on Chapter 3 and depend on the ones before them. 7, 8, the rest of the semester, the rest of the year. If you're taking 192, this trend is going to continue. We build upon our previous knowledge. And so it's important to not get caught behind in these things. If you find yourself behind, let me know. We'll chat about it. We'll make sure you get caught up to speed. But I want to make sure that we're trying to keep up pace with everything here because it is very important. Next lecture will depend on the stuff that we did today. But anyways, as we're dealing with a lot of these things, we can imagine there's going to be all sorts of scenarios that might have X and Y. There are not many things that are just going to be localized to one direction entirely. So how do we deal with these more complicated pictures? Well, we make them simpler. That's a fantastic way to do that. See, last time we talked about how we can deal with vectors and how any vector, if it's split in X and Y, can really just be recreated. If I have a vector R that looks like this, and hopefully you guys can see this one, because again, I know it's splotchy, but R might be made up of two component vectors, and it's equivalent to talk about the two vectors R of X and R of Y as it is to talk about the main vector R. That is to say, I can take the components of vectors, work on those individually, and then bring it back together if I need to. So I could rewrite my R vector, my position vector, I should say. I can rewrite my velocity vector. I can rewrite my acceleration vector and split them up into individual pieces. And then all of the operations that we've been doing so far still work on those individual pieces. The three big kinematic equations that we've been using, we just have a set for X and a set for Y. But everything else still works. If we just want to focus on X, we can still do that. If we just want to focus on Y, we can still do that. So, I've got a problem here that I'd like you to take a look at and think about a little bit. Let's imagine we have our classic toy, the rocket-powered hockey puck, right? Which is typically only used in casual play, not actual competitive play. It moves on a horizontal frictionless table. That is to say, gravity is not anything that we have to worry about today. Here, I have two graphs, neither of which are trajectory. But I would recommend you to try and draw out what the trajectory of the puck would look like given these two graphs. So, we have an exact measure of what the velocity is in each direction for this hockey puck from 0 to 5 seconds. So first, before we dive into working on the problem, I'm going to ask you guys, what do you think? What could create a scenario like this? What do we think about the directions of the motion? What caused the direction? What caused the motion in each direction? Do we have anything that could explain why we get graphs like this? What do we think? Which direction is the rocket pointing? Let's start with that. So I'm going to say here, just to be careful with things, if we're saying that it's horizontal, let's take a top-down picture. Imagine we've got a top-down kind of picture here. I think the answer I like most out of these is perpendicular to the way it's moving. That's true at the start, at least. What I can imagine here is that my rocket is giving me an acceleration in the x direction. If we are looking at a top-down kind of picture, if here is my puck, then I have to imagine that the rocket that's attached to this thing is going something like this. Right, and there's the flames. Let me make those flames. Let's highlight it orange. There we go. Now we can tell that it's actually burning. It's accelerating that way. That's the direction of our acceleration. Try and make this a complete picture as well as I can. That's the direction of our acceleration. However, when we started, we were already moving. Before the rocket was actually ignited, we were already moving because that's what v of y is telling us. So I like to split these up, and I like to kind of think about this before I dive into the problem all the way. I want to get a good idea of what is happening in this picture first. And what I could say is that v of x, all of that is being determined by the rocket. Right? That acceleration comes from the rocket. Whereas v of y, because we don't have friction or anything else to worry about, I have to imagine that somebody probably, I don't know, smacked it with a hockey puck. What else do you do? Or not a hockey puck, a hockey stick. Right? Slapped it. Now it's moving at a constant velocity in that direction, and then we ignite the rocket, and the rocket starts pushing it in x. So, with that in mind, I want you to look for these two things. First, what is the direction of the velocity, the angle of the velocity at 2 seconds? Second, how far from the origin? How far have we traveled? What is our total displacement at the end of the day at 5 seconds? So I'm going to say we're going to take the next 5 or 6 minutes here to work on this one, and then we're all going to come back together, see what we've got, and get some good answers out of this. Let's go ahead and start taking a look here. So the first thing I want to do is I want to actually give myself a picture of what I think the trajectory is going to look like. So let's go ahead and draw some axes here. Twitch off today if you are not already aware of that one. Is the resolution any better than it was right now? Sure. Resolution's good. Okay, the internet has come back a little bit from what it was, but I don't think it's enough to support both at the same time still. So, you know what? Let's not assume anything. Let's go ahead and draw out so we can see all 4 quadrants, and then we'll figure out where to go from here. So as I'm looking at this thing, I can say, okay, kind of in order here, I can see I have a pretty consistent y velocity. Right? There's no wavering, there's no changing, there's no curve to that or anything else. It's a straight line all the way across. X, on the other hand, starts at 0 and it speeds up and up and up and up and up and up and up as time goes on. So I could reasonably try to extrapolate what's going to happen in this picture, and I could say, okay, well, if the green is where the puck is moving, we start moving exclusively in the y direction. But then, as time goes on, we get a little bit more x and a little bit more x and a little bit more x and a little bit more x over time, and we get something like that. And that's not a good picture. It's not an accurate picture. But I don't really care that much because I'm not using this in any real sense. All I'm trying to do here is give myself an idea. How do I imagine this thing moving? Right? I've got 2 graphs already, but those 2 graphs, they're kind of separated out pictures. Right? It's trying to look at 2 images at the exact same time. You got to kind of overlay things to really start to see what it's going to be doing. So then I can imagine here that if I did have timestamps, then I could imagine that maybe here's like 1 second and 2 seconds and 3 seconds or something like that. So when we're asked about the trajectory, the direction of our motion at 2 seconds, what we're really doing is we're saying, what direction is this part right here? What is the slope of this part of our trajectory? That is my velocity. So what I'm going to do here, to make sure that we can actually see this, I'm going to have here's my horizontal line, and then this angle theta is what I'm really after. How do I calculate this? Assuming that I had some of these numbers, how would I actually begin to calculate this? How do we calculate an angle, the direction of a vector? Theta is equal to what? Arctangent of y over x. I agree with that. Or inverse tangent, if you would like to do that. It's the same thing. At least in the popular sense. But we're not dealing with x and y. We're actually dealing with vy and vx. So just make sure we're clear on that one. Vy and vx. Perfect. Well, I know Vy is 30 centimeters per second because, I mean, it's right there, right? That one's straight across the entire time. But the other one is a little bit more difficult to find because we can kind of see it doesn't line up at any of our grid lines. So you could kind of guess 15, 16. That's probably pretty close. But I want to make sure that we're exact with this thing. So what I'm going to say is I have 0 point right here. Over here, it hits the grid line again at 40 and 5. So that means that it's going 8 up every single time. Or we could find that information to say, hey, this has an acceleration of 8 meters per second squared. Neat. Right? That's what that actually means. But our slope, the important thing here is that our slope is 8. And if our slope is 8, then at 2 seconds, this point right here, v is equal to 16 centimeters per second. And I should have put, no, acceleration is not 8 meters per second. Acceleration is 8 centimeters per second. I need to be careful with my units. They tell me centimeters per second. That's the unit that they're actually informing us about. Question for everyone. Looking at this thing right now. V of y is equal to 30 centimeters per second. V of x is equal to 16 centimeters per second. Do I have to convert these into standard units? No. If you're not comfortable with standard units, if using units and manipulating units is something that you're still a little bit fuzzy on, then I would recommend just at the beginning of every problem, convert it to standard units. Don't even worry about it. Right? Don't have the headache of which units do I have to convert, which units can I leave how they are. Just convert everything to standard units and settle it. If you have some more experience with these units, then what I can do is I can look at this and I can say, hey, centimeters per second over centimeters per second, the units all cancel out. It doesn't matter what's inside of here, inside of my parentheses, as long as the units match. So I'm going to leave them as 30 and 16. And if I do that, and I'm writing this as a way to kind of bridge, remember that I'm saying inverse tangent is the same as arctangent, as 30 over 16, then what I should find when I actually get these numbers all together is 61.93 degrees, as I have it drawn on the picture currently. Just like that. How do we feel? Do we agree? Do we disagree? $16 is an exact value for this one. You could get away with getting something very close if you just looked at it and tried to guess. But 16 is exact in this one because what I can do is I can say, hey, I have a linear slope. And while the rest of these points are kind of in between, they are not lining up on the grid lines, at 40 and 5 seconds right up here, that spot is on a grid line. So I have 0 to 0, and I have 40 to 5. I can figure out what the slope of that line is in between, and I can find any of these values that I need. Does that make sense? Perfect. Will we ever need to find the distance traveled for something moving in an arc like that? I'm trying to think. I'm going to say probably not. Because doing so is a special integral called a line integral, where if you wanted a distance traveled, what you would have to do is you would have to integrate velocity as one piece. So here we're talking about Vy and Vx, which is great for displacement. But for distance actually traveled, you need that path integral, or a line integral is another way to call it. And both of those are a little bit more complicated. If you're in Calc 2, you might start seeing those soon if you haven't already. But we're probably not going to do too much of that stuff right now. Next semester, I know we will have some things, but almost all of those are very easy to do. We look at the easy cases. We don't look at the things that are actually really complicated. We like to make things as easy as we possibly can, which might sound like a joke to you guys right now, but I promise we do. So we've got 16 centimeters. We found part A. Now we are tasked with finding how far from the origin is the puck at 5 seconds. And I'm trying to tell you right now that doing that line integral, trying to find the distance traveled, that's messy. But we don't need that anyways. We're asking for a displacement, not a distance traveled. What is that question? Always put just the number, never put the units, because Canvas will lose its mind. Canvas has no idea what to do with units. So that's why I always try to specify what units to put it in. So, finding this displacement is really, let's imagine what we're actually doing with this thing, right? We're trying to find how much distance have we traveled in X, how much distance have we traveled in Y. Displacement is that vector between the two, right? X plus Y equals total displacement, a big triangle. That is to say, we can solve out the X and we can solve out the Y, and we don't have to worry about solving both of those out at the same time. We can treat them separately. So let me start with Y. How am I going to find my total displacement in the Y direction? What do we think? 30 times 5 is the correct number, but the exact method, if we want to describe how we're doing this, is that it's the area under the curve. We're doing an integration here. So this integration right here, if I were to look at this area, this tells me how far did I travel in the Y direction. Similarly, if we look at this one right here, this one tells me how far I traveled in the X direction. Do I have to change to standard units now? No. And I'm going to play dangerous with it. I'm going to stay in centimeters per second. So as we've got these things, what I'm going to do is I'm going to go a little bit crazy, and I'm going to leave these in centimeters per second, because if I do that, then the distances that I will be given are also going to be in centimeters. And that's not a big deal. I know how to deal with centimeters, right? They convert to meters pretty easily. So I can look at these things and I can say, okay, well, my change in Y is 5 times 30, a total distance of 150 centimeters. My change in X, 5 times 40 times 1/2, because it's a triangle, and that should give me something like 100 centimeters. That is my displacement in the X and the Y direction. To find the total displacement, as I need it here, what I'm going to say, my total displacement, delta R, looks just like this. Delta X squared plus delta Y squared. Plugging these two things in together, what we should find at the end of the day is a total distance of 180.3 centimeters. And if we would like to see a picture cutting out, man, even the audio now, the audio was like the one thing that we had. Man. Frozen again. Past 15 seconds are missing. Excellent. Okay, let me just say that again one more time then. Am I back now? Is it kind of here? Okay, back now. In the moments that I have with you, what I'm trying to describe, that our total displacement, delta R, is essentially summing up the two legs of the triangle delta x and delta y. If our final position is up here and our initial position is over here, then all we need to do is Pythagorean's theorem to actually find what that total displacement is from our initial position. So, how do we feel? Do we have any questions? Is there anything else that I cut out at? 5 and 40 are not what we're going to be doing for some of those. What I've got in here, I've got my displacement in the x direction, my displacement in the y direction. It's putting those two together. To find delta x, yes, 5, 40, and 1/2. Because it's a triangle, we're only getting half of that space. Okay. So I'm going to say, let's keep moving on for now. Let's go ahead and look at the next couple things that we've got going on in here. So, we've already kind of stated right from the beginning of the course that we are mostly going to be looking at circumstances of constant acceleration, right? And that is going to remain true. Just because we are in 2 dimensions does not mean that much of that's going to be changing. Now, it just means we'll have kinematic equations, but in 2 columns. Over on the left side here, we've got all of our kinematic equations in regards to x. Over on the other side, we've got all of our kinematic equations in regard to y. And notice the individual variables here. In the x direction, there is no mention of y. In the y direction, there is no mention of x. Because again, you can treat the components of vectors independently. That's a wonderful feature of those things. All of these kinematic equations are just kind of playing into that fact that these are vectors and that the components of vectors don't depend on each other. The only thing that actually ties them together is going to be the fact that there is a time that is shared between them. If I toss a ball and I measure its x and y position in time, right, that's specific right there. I measured it with my stopwatch at that particular time. Everything else, velocity, acceleration, position, is allowed to be separate, but time is shared between the 2 columns. So then, when you're working on a lot of these problems, you don't have new equations that you necessarily need to grapple with. You just have more of the same as before. And you need to figure out what we can do to tie these 2 together. There might be conditions on one column and not conditions on the other, and you use the condition column to find some things out about the other one. I don't know if I'm going to be able to, it might be kind of blurry no matter what, so my recommendation is still going to hold of have the slides up on your own computer right now. That will be probably the best way to approach these things, because there's a lot of stuff going on in these. So that's how we're going to be treating a lot of these problems. We're going to be approaching these in the idea that having 2 columns, right? One of them for x, one of them for y, and I can look at both of these, and I don't necessarily need to move them into each other. I want to separate them out so I'm at least a little bit organized, but I know that time will be shared between them. So, one of the very, very common cases you're going to see is going to be projectile motion. And projectile motion is very handy. We use it all over the place. We're going to have a lot of problems to do with this thing, but there are certain conditions that get applied to it. Being that most of the time, there is no acceleration in the x direction. Nothing going on in x. That means any x velocity we have is constant throughout the entire trajectory. On the other hand, y does have an acceleration coming from gravity. So that acceleration is going to be negative g, which is something we have seen already. Now we're just combining these 2 ideas. If we have some sort of velocity vector, some initial velocity pointing at an angle, any angle that we might have, then what we can say is that that velocity gets split up into Vx and Vy, and those are our 2 initial velocities, our 2 accelerations, a position, and a shared time between the 2. And that is typically enough to get through all of your problems. So, here's a little bit of a description. That's kind of how I like to approach these things. A very similar kind of thing here is what gets suggested in the book. This is what our good friend Randy talks about as his method of solving a lot of these problems, what he does for these things, and it, I think, compares very well to the things that I like to do for a lot of them, right? Notice that he keeps these things in 2 separate columns. It's much easier to deal with when it's 2 separate columns. But for the most part, it's just kind of going through, this is in the book. You have seen this, even if you have not read it. You know, if you're looking for a guide, how do I go through these problems step by step? This is not a bad way to approach these. But I want to try this thing out. Let's imagine we have a rifle aimed horizontally. Not up, not at an angle, horizontally. Shooting at a target 50 meters away. We are not trying to adjust for the drop of the bullet or anything else like that. We fire. The bullet lands dead on in the middle, but 2 centimeters below where we had been aiming. Draw a picture. Label all of the variables that you know you have. Randy's a good friend. Come on. He wrote this whole book for us. But anyways, find the flight time. How long was it in the air from when it was fired to when it collided with the target? And then using that, find the speed of the bullet as it left, the initial velocity. I'm going to say 7 minutes, and then we'll look at this one. I think I'd like to start taking a look at this one. All right, and I'm starting to see some numbers I think I agree with a little bit more. So for reference here, one thing that you can do for a lot of these velocities, so a bullet's a fast-moving thing, realistically, right? Those are typically not going to be going very slow. The speed of sound is right around 343 meters per second. So that's kind of a nice little reference point, I think. When you're talking about things like jets or bullets, should they be more or less the speed of sound or, you know, like a bit above? I think that would seem reasonable to me within an order of magnitude. I would argue that seems good to me, right? Less than Mach 10 because Mach 10's not a super common speed. It takes a little bit to get to speeds like that. Versus some other things, if you ever see a speed of something you don't expect to be going very fast, and you see that thing up to 300, that's like, you know, that's a little bit high. So I'm just saying that mostly to think about some of the numbers that we've got here. That is another reference point. As you're comparing a lot of different things, somebody walking at a quick pace might be like 2 meters per second or something. There's a wide variety of things, but these little reference points help us look at a number. We have calculated a number. We look at that number. We ask ourselves, does that actually seem reasonable, or is this just a bunch of nonsense? But anyways, let's take a look at this thing. So probably one of the most important bits about this is actually going to be drawing out this picture, because realistically, that's going to kind of guide a lot of our solving here. So let's start by drawing the rifle. I asked for that to be in black, please. So there's like the barrel, a stock, and a trigger. Look at that, right? Quality. Now, what we also have is it's firing off a bullet. So let's draw that like this. That bullet is initially fired off horizontally. Very important detail. So let me do this right now. Let me just say horizontally, this is positive Y, this is positive X, right? Standard directions. Nothing crazy here. So if it's fired off horizontally, going something like this, probably not very well, but that works. This is our V naught vector. Where is it going? It is going to take this line all the way across. And what I'm going to do is I want to make this a dotted line because this is like the pure horizontal kind of line. So it's a dotted line. This is saying, hey, it might move this way. I don't know. We'll see. What do we actually know, though? I've got a good feeling it's not actually going to do this. It's fired at this target, and I'm going to try and make it look like it was actually fired at the middle, something like that. But as it traveled, what actually happened. We didn't hit in the middle, despite the fact that that's where we were aiming. That was our initial path, our initial direction, but gravity had something else in mind. It dropped by 2 centimeters, or 0.02 meters. And the reason I am converting this time is because one of my other distances was already in meters. So I'll just, might as well take everything to a standard unit. So our actual path probably looks something a little bit more like this, roughly speaking. None of this stuff is drawn to scale, but again, it's just supposed to be helpful for me. This distance right here, this delta y that we've got between the two, how far we have fallen, versus delta x, how far we have traveled horizontally. Okay. Now that I've got this, let's start going through and talking about these variables that we actually have. I've got a decision to make. And I think the easiest way to make this decision is to say, well, we could say x, let's go with delta x. Let's say delta x was equal to 50 meters. Delta y dropped by 2 centimeters. So I'm going to put that as a negative 0.02 meters. And that's an important distinction, right? Because as I have drawn, y was going up. So I want to make sure that if I have gone against y, if I have gone down relative to the direction I said was y, that's a negative value. What else do I know? After the bullet has been fired, it has left the barrel, nothing else pushing on it from the back, nothing is touching that bullet until it hits the target, right? Nothing else. So what I can say there is that, hey, there's really not many other forces here, right? A of x, that's 0. Gravity will be pulling down, but we know how to deal with gravity. That means the acceleration in the y direction is just negative g. But there's nothing pushing on it from behind. There's nobody trying to stop it, hopefully, right? We're just going right at the target. So if nothing is going on in the x direction, the acceleration in the x direction ought to be 0. What else do we know? The way that we fire this thing, do we have any velocity in the y direction? What do we think? No. That's an easy one. That's going to make our life substantially easier to deal with. That also means that my x velocity is equal to v naught. Any initial velocity we had was exclusively pointing in the x direction when we started. And I've highlighted that one in red because we actually know that initial velocity. My hint is no, we do not, because that is part B of this problem. Part A is to find how long was it in flight. The second part is finding what is that velocity. So let's start taking this thing apart. We need some kinematic equations. We're going to try and figure out which ones work, which ones don't. So what I'm going to do is I'm going to break this up into 2 columns. I'm going to start with my x direction. What I could say is that delta x is equal to v of x times t plus 1/2 a of x t squared. Cool. That's 0. There's no acceleration. Delta x is equal to vx times t. I could take this one more step down if I really wanted to. The delta x is equal to v naught times t. Now let's think about these things. I know what delta x is. That's the 50 meters that was given to me. V naught, unknown. T, unknown. That's it. I can't do anything else with that equation right now. Move on. I could also imagine perhaps Vf of x would be equal to my initial x velocity plus acceleration in the x direction times t. How much information did that equation just give me? Does it tell me anything? Any guesses here? No, it was useless, right? Acceleration in the x direction is 0. Of course the final velocity equals the initial velocity. in the x direction. That information is useless to me, though. That equation does not give me any new or useful information. Similarly, we can imagine if we take the next step down, that last kinematic equation, Vf squared, that's going to do the exact same thing. The acceleration is still 0. Just because it doesn't depend on time doesn't mean it's still not giving us any new information. So I'm not even going to bother with these ones. These are useless equations to me. There's nothing I can possibly do with these to make them useful. Acceleration in the x direction is 0 because there's nothing else happening in the x direction. As we have drawn this, this is a perfect case of projectile motion where the bullet is traveling in one direction, gravity is pulling it down, but nothing else is touching it. There are no other forces at all. So, my sense here is that I have exhausted everything I could possibly get out of the x direction. And it's not, yeah, I didn't get a lot, right? I wrote down an equation, and maybe this is useful, but right now there's no new information that I can pull from this. So I'm going to say, all right, well, not a big deal, because I still have another direction. I still have the y direction to deal with. So let's take a look at this. We could say in the exact same way, delta y is equal to v of y times t plus 1/2 a of y t squared. Okay, well, I know that v of y is 0, so that part gets canceled out. Then let me take this down a step and let me say, okay, well, delta y must be equal to negative 1/2 g, plug that in, might as well, times t squared. I don't know t, but that's it. We found our golden ticket. That is how we can find out time. Now, I have another question for you. This is not part of the problem, but let's imagine a part C. Is the final speed of the bullet less than, equal to, or faster than the initial speed of the bullet? What do we think? Less than? Less than? Let's talk about before it hits the target, right before it hits the target. Because again, when we actually get into collisions, that's a very, very different scenario. We will talk about collisions eventually, but not right now. So the instant before it hits the target. 2 answers less than. Anything else? A little bit of variety here. Nobody thinks equal. And I would agree with that. It's certainly not equal. But I have to think about it like this. When I started this, my initial velocity v0 going in the horizontal direction. When I ended this, my x velocity was still v0. There was no acceleration in the x direction, so there was no change to the velocity in the x direction. Is there a speed in the y direction, though? Is there a velocity in the y direction at this point? There absolutely is. Why else would we have moved down? We could write that out. Let me do this in gray, because this is not part of the problem at this point. But this is a nice little thing to think about for considering, because we will have other problems that will ask you to find these speeds. My final velocity in the y direction is equal to the initial velocity in the y direction, otherwise known as 0, minus g times t. That right there tells me I have a velocity in the y direction, a speed in the y direction, and since the x direction has not changed at all, we did in fact speed up as we fell down. Now, if anybody wants to complain about air resistance, that is not entirely unwarranted, but not that big of a deal. Realistically, we ignore air resistance in most cases for 2 reasons. For one, because we're typically looking over scales where it is not a very large factor. 2, it is super difficult when it is a factor. There are multiple terms of air resistance, and those terms of air resistance, I think there are 3 in total. and they have different weights depending on the shape of your object. One of them depends on v squared, one of them depends on v cubed, and one of them depends on v to the 3/2 power. That means you could come out with an acceleration that looks something like this, some constant times your velocity squared. It gets a little bit recursive, right? Because acceleration is your change of velocity, but the velocity depends on the acceleration, and it's not good. It's very not good. So we're going to try and look at only the cases, and we're going to mention, right, in the case of the flea problem, the flea is light enough and small enough that air resistance is actually a factor. But for the most part, it is not going to be something that we ever need to worry about. As we have it written out, if this was done in a vacuum, if there was no air or anything else, we would have seen the speed of the bullet increase. But again, that's not actually part of our problem right now. That is just a conceptual thing that I did want to go over while we were here. The last part of the problem, we say we need t. We have one equation that is ready to solve that out for us. If I solve out for t in this thing, I move over the 1/2, I divide by the g, and I have a negative. Oh no. Have I broken it? Did I just find an imaginary time? Ooh, split opinions. No, I have not, but why? Time is still real, but g is not negative. G is a positive 9.8 meters per second squared. Acceleration is negative g. Gonna try and break you guys out of that habit. G is a positive value, and the reason that we use it as a positive value because it's going to show up in a lot of different places. Saying that g is positive 9.8 gives us a lot of flexibility in how we use that variable in different places. We're going to have a lot of different places where g is going to show up, so I implore you, please remember, g is a positive number. The acceleration is negative g. So, on to the actual point, though, and some people have it here. Delta y is a negative value. So the negative cancels out with the negative there. Everything else is positive inside of that thing. We can plug in all of our numbers together, and when we actually go through and crunch them out, we should find a total flight time of 0.0639 seconds. Okay. So what I'm going to say here is today is a shorter lecture, and that was intended because there is a lab today. And there is a lab today where you are actually participating in the lab. No simulations or anything else. You are doing this. Your lab equipment is whatever you can find around you right now. I'm not going to ask you to stick around for this one, but what I am going to say is that if you go to the Canvas calendar on the homepage right here, highlighted in green, we have the Finding G lab. Right, we had a little bit of discussion here of, is it going to be 10? Is it going to be 9.81? Is it going to be 9.8? And this is your opportunity to test that for yourself. So if you click on that thing, what you're going to find is a very, very short description and a link to a Google document where you can download your own copy and fill it out. Do not ask permission to edit my master copy of the lab. I will not grant it. You might also run into issues. It is currently set up so that it is accessible for Miami emails only, so that if you run into an issue, check for that one. If you're signed in with your Miami email, you should be able to access it no problem. It is on, if you are going to the, it should show up for one in your little to-do list thing, but if you're on the main page calendar, it's going to be right here highlighted in orange, Finding G Lab. As soon as an assignment is ready for you guys, it gets highlighted in orange. So you can click on it from that calendar homepage. But if you have, if you are taking the course with a roommate or a friend or anything else like that, you are more than welcome to work together with them. I have no problem with that whatsoever. If not, it's not a big deal at all. Just do this yourself. A pro tip, as you're measuring things, I'm assuming that not many people have meter sticks just lying around their house. I don't have a meter stick. I usually have a ruler. So if you're trying to calculate out a lot of these things and you're using a wall, if you're following the video and you're maybe using a door jamb or something else like that, my pro tip for you is that if you take a pencil, you can write on the wall and mark little tick marks to get better measurements. And then you can just erase afterwards. And I know that sounds kind of crazy at first because we have been taught our entire lives to not write on the walls, but I promise graphite rubs off of walls. You can lick your thumb and just rub it off the wall if you need to. So that's my little pro tip, because I know a lot of people don't have necessarily meter sticks or anything, but even if you want to use like pieces of paper, knowing that the side length of the piece of the paper is 11 inches, you can do that to get some good thing right there. The lab is due by Friday night. But it should be pretty short. You shouldn't need to spend too much time on it, but it'll be a little bit of fun. But that's all I've got for today. So if there are still questions or anything else, I'm more than happy to stick around, talk about any of these things that we've got, homeworks or lab issues or anything else like that. But otherwise, go off and get started on this thing. Have some fun with it. And have a good one. Thanks for being here. Absolutely. Thank you, guys. Oh, I didn't find the final answer for this, did I? Yeah. I did this last time too. I like went into a really long description, then I'm like, oh wait, I didn't actually solve out part B. Where do I have this thing? The final answer, when you plug in and solve out for it, it's 782.6, what I had. If you had a slightly, if you rounded the time or something else like that. Yeah, I just saw the comment on that one. I didn't solve that. What was the problem you were talking about, though? Okay. Yeah. We have one expression that's got, well, now that we have t, we have our one expression that has v naught as an unknown. We can plug that in, and we've got it. Absolutely.